Okay, good day. So today's presentation is about analyzing samples in the clinical chemistry laboratory. And we're going to look at the instruction sheets of how to successfully analyze samples and what are the information on that instruction sheet, what does it all mean, and how do you interpret it, and how do you read it, and what information do you use for a successful analysis of a sample. So this method is from Randox. Randox is the manufacturer. There are different manufacturing companies. Another one is Beckman Coulter. They specializes in automated analyzers and reagents as well. Another manufacturing company is Abbott. You have Roche as well, and you have Johnson & Johnson. So there's a whole host of different manufacturing companies. The one that we're dealing with right now is the Randox company, and we got this method from them, and we're going to work on we're going to analyze or talk about the package insert of albumin. So information that is given is bromocresol green. That indicates the method for the albumin analysis. Then it also tells you can use it for manual analysis and you can use it for automated analysis. RX Monza is the analyzer that is manufactured by Randox. Then other information is the intended use. It is for the quantitative analysis of albumin in serum or plasma. So in vitro, meaning quantitative analysis in the laboratory, in the lab, outside of the human body. In vivo is inside the human body. So, and this product is suitable for manual use and on the RX Monza as well. Then the next item is catalog number, and the catalog number just indicates that this is the kit identifier for the manufacturer. So each kit and each reagent will have their own catalog number, and even one reagent might have different catalog numbers as well. So if you look at creatinine, for instance, here you see two catalog numbers. Here you see two catalog numbers, CR2336, and this is the contents of that kit, and CR2337, and this is the contents of that kit. You see, so this kit has about 4 times 50 ml reagents, and this has got a bigger volume. It's got 4 times 100 ml reagents total volume. So the kit, the catalog number just indicates the kit. It is a kit identifier for the manufacturer to label. When you talk about AB362, then he knows exactly you're talking about albumin. Other information on this sheet is clinical significance, meaning what is the clinical significance of albumin in the human body. Okay, so here it gives a whole lot of physiological information explaining the purpose of albumin in the human body. The next piece of information is principle. What is the principle of the test? And in this case, it is the measurement of serum albumin, which is based on the quantitative binding of BCG. And this BCG binds to the albumin in the sample, and that complex that is formed gives a color reaction, and that color reaction can be measured at a specific wavelength. So in this case, it can be measured at 578 nanometers. So it has maximum absorbance at 578. But if you're talking about the wavelength, then different methods have different wavelengths. So depending on the concentration of the constituents, concentration of the buffer, concentration of the active reagent, they will all have different wavelengths at which it can be measured. The next piece of information on this sheet is sample preparation and collection. So here it tells you the type of sample that you can use with this method, and in this case it is serum, or you can use heparinized plasma or EDTA plasma. So heparinized plasma is the green top tube, EDTA plasma is the purple top tube. And then it says normal procedures for collecting and storing serum may be used for analysis of this method. So this sample serum is stable for 3 days at 2 to 8 degrees. 2 to 8 degrees is fridge temperature, or the serum can be kept in the freezer for 6 months. Freezers minus 20 degrees centigrade. Then it also gives information about the reagent composition. The reagent, the BCG reagent, it consists of R1, and that R1 consists of BCG concentrate, and that concentrate consists of or the R1 is labeled BCG concentrate, and that consists of a buffer with that concentration, 75 millimole per liter, and at that pH. And it also consists of the bromocresol green, the indicator reagent, at that specific concentration, 1.7 millimole per liter. Then it also consists of a Bray 35 reagent, and this Bray 35 reagent is a non-ionic solution, and this reduces the absorbance of the blank. So it actually helps with preventing turbidity of preventing the blank from causing turbidity in your sample. Then it also has some preservative, and manufacturers in order to prevent others from copying their reagent, in this case they don't say what the preservative is and what the concentrations of the preservative is. And likewise with this one, Bray 35, they don't say what volume they put in, and they don't say the concentration, but usually this Bray 35 is about 30, it's a 30% solution. So if we had this concentration, then we could make the reagent ourselves, and then we don't have to buy from Randox. But in this case, they didn't give us the reagents of the Bray 35 and the preservative. So this is the contents of the R1 reagent. And if we go down, okay, just go to the top, then other information that is on the sheet is safety precautions and warnings. And here it just tells you general safety precautions that you have to adhere to, such as do not pipette by mouth. Okay, I don't think people do that anymore because we don't use that rod-like pipettes anymore, those big rod-like pipettes anymore. We use the automated pipettes that ranges from 200 microliter to 1000 microliter, and other pipettes where you have 10 microliter to 100 microliter. So but in essence, is the safety information is exercise the normal precautions required for handling laboratory reagents. Don't let it get onto your skin, don't let it get into your eyes or your mouth or any part of your body. Then a note of caution when you work with the standard. what they say is that the standard is human source material from which this product has been derived, and it has been tested for various diseases such as HIV. It has been tested for hepatitis B antigens and for hepatitis C virus as well. So those are quite pathogenic, virulent viruses, and what the manufacturer says is that this standard has been tested for those pathogenic diseases, pathogenic viruses, and it has been found to be non-existent in this sample. But then it gives a sort of a disclaimer: since no method can offer complete assurance as to the absence of infectious agents, this material and all patient samples should be handled as though capable of transmitting infectious diseases and disposed of accordingly. So just as the type of sample that you're working with, you don't know what infectious material is in that sample, so therefore you protected your hands and your body by wearing gloves, and you keep it away from your eyes and your mouth. In the same way with this standard, normal safety, health and safety precautions must be applied. Protect your hands, protect your face, protect your mouth, and protect your eyes. Then other information that it gives for this on this package insert is: the reagent must be used only for the purpose intended by suitably qualified personnel under appropriate laboratory conditions. So once again, it's a disclaimer, manufacturer trying to protect themselves that in case you contaminate yourself, the manufacturer, they told you this is dangerous material and be careful. So just be aware of that. Then other information, stability and preparation of reagent and standard. So here it will tell you how stable the reagent is. In this case, reagent R1 is stable for 3 months at room temperature, and it also tells you how you must prepare the reagents. Dilute the contents of 1 bottle with 87 ml of distilled water. So the reagent comes in with a certain quantity, and in this case the total volume is 100 ml, but it doesn't come with 100 ml of reagent. It comes with less. You have to add 87 ml of distilled water to make it up to 100 ml. So this is one way of what they're talking about when you say preparing of reagent. If you look at creatinine, for instance, the preparation of reagents, here they say R1A, this is for creatinine, R1A contents is ready for use, so you don't have to do any preparation there. But with R1B, you have to reconstitute the contents of 1 vial of substrate R1B with a portion of R1A. Transfer the entire contents to buffer R1A, rinsing vial R1B. So basically they're saying that you must transfer R1A, or you must mix R1A and R1B, and then that will be your active reagent. So R1A, R1B must be mixed, and then that reagent is stable for 30 days. So different instruction sheets will have different different methods, will have different ways of preparing the reagents. Sometimes they will say the reagent is ready for use, so you don't have to do anything, you don't have to add this or that, or you don't have to add water. And in this case it tells you you must actually at 87 ml of distilled water. Then about the calibration standard, the contents is ready for use and it is stable up to the expiry date when stored at 15 to 25 degrees. In other words, at room temperature. Now, the calibration, the cal standard or calibration standard, comes with a separate package insert. Let me just go down to that. Here is albumin standard, albumin calibrator, and each calibrator comes with its own lot number. It tells you the size and the volume of the calibrator. So this is only 5.5 ml, a smallish tube. Then it also tells you what you should do, contents is ready for use, and the concentration, and this is very important, the concentration of the albumin standard is 46 gram per liter. So let me just highlight this. So we're not using gram per deciliter, we're using the SI units, which is grams per liter. Okay, so and you must remember this, keep this piece of paper with you. If, for instance, there was no standard with this reagent, then you can use a different standard as well. So you can use a multi-calibrator, for instance, and in this case, a multi-cal, which is multi-calibrator, meaning that there are more than one analyte within this calibrator, and there's the lot number of this calibrator, there's the reference number. The reference number just indicates it is the manufacturer that says this reference number belongs to this item, multi-cal. So the lot number will change with a different batch. Every batch has a new lot number, and of course there's the expiry date. Okay? So this is an old one. It's just an example that I'm giving to you. So this multi-cal has got multiple analytes inside this sample. You can use it as a calibrator for alkaline phosphatase, ALT, amylase, AST. You can use it as a calibrator for CK, gamma GT, LDH. There's different methods of LDH, the IFCC method, and there's the DGKC method, and lipase and albumin. So, and this method is bromocresol green. So you can just be on the lookout for the method as well. Sometimes they have more than one method, bromocresol green or bromocresol purple. That will also state here. So then you can look at the value for the specific analyzer or the specific method. So in this case, let's say we're using the P400 analyzer. There's no manual method multi-cal result that is listed on here, so we're just going to go with the P400, which is the analyzer that we have in the laboratory. And if you look at which is in this column, and if you go down to albumin, then you take this value, gram per liter, 33.5. You'll see that the values are very close to each other, 34.1 for the different analyzers, and it should be, there's just minor variations if you use a different analyzer every time. So, but if we were to use the P400 analyzer, and then and then we can use this result, 33.5 grams per liter. So to get back to our package insert, so materials provided is the BCG concentrate and the albumin standard. That is what is in the kit. Then the materials required but not provided is pipetting devices. So you must be able to pipette 10 microliter and 3000 microliter. You need a timing device, and you need a water bar, something to bring the temperature to 20 to 25 degrees. If, for instance, that mostly applies to colder climates, Russia, for instance, which is a very cold place, if they don't, they either have to specify that the temperature must be brought to 20 to 25 degrees, or Sweden in the winter, or any place where it's extremely cold, even in Cape Town when it's extremely cold, then you have to make sure that the temperature is brought to 20 to 25 degrees, which is a room temperature. Then other material that you also need is a spectrophotometer that can measure between 600 and 650 nanometers. And then they also talk about, say, you must have controls, multi-Sierra level 2 and level 3 controls. And they talk about Randox calibration serum level 3 standard. But we've already have a standard which is in the kit. So this is just an extra standard. So you don't have to have another standard to do this analysis, seeing that you have already a Cal standard. So with the multi-Sierra controls, that is a manufacturer specific item. So in this case it is a Randox item, Randox controls, multi-Sierra controls. If you don't have the Randox multi-Sierra controls, then you can use something different. And we have in our laboratories we have N controls and P controls. N represents normal control, and P represents pathology control or abnormal control. So, and this manufacturer is ABX Pentra, and it is made by Hariba Diagnostics, Hariba ABX Diagnostics. So in control, so you must have two controls, a normal control and an abnormal control. And in our laboratories we're going to use N control and P control. And once again, there's the lot number of this control, and there's the expiry date. And reference number is just a number that the manufacturer uses to identify the item. And once again, each lot number, each batch of controls will have a different lot number. So lot number or batch number. And in each set of controls there are multiple analytes in there, so you can use it for more than one item. It would be very expensive if you use one control for one analyte only. Then you're going to sit with a whole range of controls, and you have to, if you want to do albumin, you must get a control for albumin. If you want to do creatinine, you must go and get a control for creatinine. It will be very expensive. So therefore the manufacturers, they've used one sample and they've determined the range of each analyte in that one control sample. So therefore you will have all these tests in that control sample. And here's the control values for albumin. So we're going to use this one, the P400, which is the Pentra 400 analyzer, and the range is 39.6 to 48.6. Okay, and that is the mean. Let's go to the top. So that's the target value, the mean, and that's the confidence range, and that is 1 is the value. So if you just go, so if you, let me just write down, so this is the mean. That's the mean, and this is the confidence interval, the range, and this is 1 standard deviation. So if you want to go to 2 standard deviation, you multiply that with 2. If you want to go to 3 standard deviation, you multiply that with 3. Okay, so that's minus 1 standard deviation, and that is plus 1 standard deviation. Sorry, that is incorrect. That is the standard deviation, 1 standard deviation is equal to 1.5. So if you times that with 3, it will be 4.5. So if you add 4.5 to 44.1, then you get with 48.6, which is 3 standard deviation. So this is minus 3 standard deviation, and this is plus 3 standard deviation. So this represents the 1.5 grams per liter represents 1 standard deviation. Okay, so that is the in control, and if you go to P control, same thing, lot number, expiry date, reference number, and the various tests. For albumin, in this case, 30.8 grams per liter. That's the 3 standard deviation range, minus 3 standard deviation, plus 3 standard deviation, and 1.1 gram per liter represents 1 SD. So if you multiply that with 3, you're going to get 3.3. And if you add 3.3 to 30.8, you're going to get 34.1. And likewise, if you deduct 3.3 from 30.8, you're going to get 27.5. Okay, so that is the multi-serial. Then the procedure. Now, seeing that the manufacturer, Randox, they told us before that this method can be used for an automated method, and it can be used for a manual method. So in this case, the procedure for this one is for the automated method, RX Monza, the analyzer RX Monza. So we're not going to use the RX Monza method, we're going to use the manual method. So if you go down, then you'll see for manual use. And for manual use, we're going to use the wavelength 630 nanometers. That wavelength there, that is for the automated method analysis. So you're going to set your spectrophotometer to 630 nanometers, and you're going to use a 1 centimeter light path, and you're going to do it at room temperature, and the measurement is going to be against reagent blank. Now with this, here you have to find your way of viewing, of visualizing how you're going to do this. I find it easy to do it this way. Let's say you draw tubes. Tube 1 is going to be your reagent blank. Tube 2 is going to be your standard. Tube 3 is going to be your control, and tube 4 is going to be another control, in control, P control, and tube 5 is going to be your sample. Okay, now in each one of these, in your reagent blank tube, you're going to add 3000 microliters of the reagent that you prepared, and you're going to add 10 microliter of distilled water. So that's going to be your blank, and then you mix properly. So in each one of these tubes, 1, 2, 3, 4, 5 tubes, you're going to add 3000 microliters of reagent R1. And in each one of these, you're going to add specifically that analyte that you want to test, or the sample containing the analyte. So in the next tube, you're going to add 10 microliters of the standard into this tube. In this tube, you're going to add 10 microliters of in control. In this tube, you're going to add 10 microliters of P control. And in this tube, you're going to add 10 microliters of your sample. So you're going to sit with 3000 microliter of reagent and 10 microliter respectively of each sample. Water, standard, in control, P control, and patient sample. Then you mix that properly, and you incubate for 5 minutes at room temperature. So you just leave it on the bench and you incubate it for set your timer for 5 minutes, and then after the 5 minutes you measure the absorbance of the sample, of the standards, and of the control against reagent blank. So the first thing that you're going to do with your spectrophotometer is blank your spectrophotometer. So you've set your spectrophotometer on 630 nanometers. Then you press 0. Now you have your starting point for your measurement. Then you add your standard sample that you put into a cuvette, and you put your cuvette in your spectrophotometer and observe what the absorbance is, and you record that. And you do the same for the in control. Put it in a cuvette, put it in a spectrophotometer, observe what the absorbance is. P control, observe what the absorbance is, and your sample, observe what the absorbance is. You don't blank between each measurement. So once you've blanked your spectrophotometer initially, then you use it for the remainder of that test. So you only blank once, and then you do read your absorbances of each of the samples. So once you have your absorbance values, so now you can calculate what the concentration is, because this method is based on Beer's law, and Beer's law states that the absorbance the concentration of a substance in solution is directly proportional to the absorbance of that substance in a 1 centimeter light path. Okay, so, or you can say the other way, the absorbance of a substance, the absorbance of a solution is directly related or directly proportional to the concentration of that substance in solution in a 1 centimeter light path. Okay, so now you can calculate, use the derived formula, derived Beer-Lambert formula, whereby you say concentration, so concentration equal the absorbance of your sample divided by the absorbance of your standard times the concentration of your standard, and the concentration of your standard is that one that you had, 46 gram per liter. So if you used the Randox standard, then you're going to use 46 gram per liter. If you use the multical, then you're going to use 33.5 gram per liter. But in this case, let's say we've used the Randox calibrator. So then the standard absorbance value is always going to be the same for this analysis, and the concentration of the standard, that's also going to be the same, and the only thing that will change is the absorbance of the sample. So you're going to put, if you want your absorbance of your in control, that absorbance or the concentration of your in control, that absorbance of your control goes in here, divided by that times that, give you the concentration of your in control. P control absorbance, that goes in here, divided by standard absorbance times concentration of standard, and same with the sample, absorbance of sample divided by absorbance of standard times concentration of standard. Okay, so with this, with the analysis, with any analysis, you must do the controls first, because the purpose of the controls is to determine whether your method is reliable and whether your method is acceptable, is going to yield acceptable results. So therefore you're going to do your standard, and then you're going to do your controls, your in control and your P control. If it's a different manufacturer, such as Beckman for instance, they have decision controls. If you use Randox controls, and then they have multi-series controls. So you're going to do your controls first, and then find out, is your values that you obtained, is it within this range? Is it within the acceptable range? Did I go past? Chlorobally, chloride, cholesterol, creatinine, glucose, lactate, triglycerides. So what happened to albumin? There's albumin. So the controls that you calculated, that concentration must be measured, must be checked according to this 39.6, 48.6. And it's always a good idea to plot your values on a Levy-Jennings chart. So for instance, you would draw your chart, and that's the mean. Then you have your mean is 44.1, 44.1 grams per liter. The units are very important. And then minus 3 SD is 39.6. So 39. And your plus 3 SD is 48.6. Then in order to do your two standard deviations, you're just going to multiply 1.5 times 2, and then you're going to get your 2 standard deviation. You're going to get your 1 standard deviation and then your 2 standard deviation. So then you plot your value. Let's say you obtain an albumin concentration of, for argument's sake, 47.5. So 47.5 would be around about there. So let's say that is 2 standard deviation, that's 3, that's 47.1. 47.1, let's say that's 2 standard deviation, and so let's say this is your N control, and your P control, you do the same. You plot your N control and your P control, and then you compare the two, and you see whether any of the Westgard rules are violated. So you look at the rules across the different controls and individually. So individually, per control, you look at the Westgard rules and you compare it with the other control as well, the P control that you did on the same sample, or together with the same sample, and then you check whether any of the Westgard rules has been violated. Okay, so once you've checked your controls and you find that your controls are within the reference range, and then you can start analyzing your patient sample and obtain the absorbance and plug it into the formula and obtain your concentration of your patient albumin. So other information on this sheet is quality control, Randox, assay, multi-seer. Okay, we've talked about quality control. You must run a minimum of 2 controls on your samples, and all they say is if your controls are out, and then you must look for this type, for these things. Check the light source, check whether the instrument is clean, and equipment, etc. So that's just troubleshooting if your controls are out of range. Other information on this sheet is what substances could interfere with this test. The following analytes were tested up to the following levels and were found not to interfere. Bilirubin at a concentration of 500 micromole per liter, total bilirubin 500 microliter, that is quite high, because the normal range for bilirubin is it's about 2 to 20, 21 or 25 micromole per liter. So they found that the high concentrations of that doesn't interfere with this method. And bilirubin gives an ecteric color, a dark yellowish color, a very intense yellowish color. So that color doesn't interfere with this method. Other things that they tested is intralipid. An intralipid solution is an intravenous solution that is given to patients, and they found that 1.2%, if patients receive 1.2% of this solution, intralipid, it doesn't interfere with the method of albumin determination. And the same with triglycerides, 22.75 millimole per liter, which is quite high. The normal for triglycerides is about 1 millimole per liter. And triglycerides, it gives a fatty substance, so it gives a very turbid appearance to the sample. So you would think that it would interfere with the absorbance of the sample, but this manufacturer is saying that even though the patient, even if the patient had a high concentration of 22.75, it wouldn't interfere with the absorbance with this method. And hemoglobin 6.6 grams per liter. Other information they give is normal values in serum, so in other words normal values of patients. And albumin normal value for adults is 38 to 44 gram per liter, and for neonates, newborns, it is slightly less, 38 to 42 gram per liter. Then they also say it is recommended that each laboratory establish its own reference range to reflect the age, sex, diet, and geographical location of the population. Now, if you're a startup laboratory, a relatively new laboratory, it's going to be a little bit expensive for you to determine your own patient reference range. So, for you as a startup laboratory, as a new laboratory, you can use the national reference ranges that is given. So maybe a reference range that the NHLS is using, but you use a reference range that is used nationally. The purpose of each laboratory establishing its own reference range is because values will, a normal range will differ from population to population because of the environmental factors and the age difference and the sex difference, etc. For instance, there might be people that eat a certain type of food in Africa or in South Africa. Maybe they like a lot of curry, or maybe they like a lot of vegetables. So, and if you compare that range with people in Asia, for instance, maybe they don't like a lot of curry and they don't eat a lot of vegetables, for instance, or they eat a certain type of vegetable, then that will change the reference range of that population group. So you use the reference range that is local to that population group. In other words, reference range relating to the South African population. Once you're established as a company, as a laboratory, then you can determine your own reference range for the population that you serve. Okay, other information on the sheet is specific performance characteristics, and here they talk about the linearity. This method is linear up to 75.5 grams per liter. Now, linearity, so this takes you back to first year lab instrumentation, where you dealt with where you had to draw the standard curve of a substance, of a specific solution. Maybe you drew a standard curve of potassium dichromate, or maybe use some other substance to draw a standard curve. So, and that standard curve at a specific low concentration, you will have erratic results. And a specific high concentration, you're also going to have erratic results. So you're only going to use that value where you find a linear line from the low value to the high value. And anything out of that linear line will give you meaning it is non-linear. So let me just draw something here. So if you draw something like this, let's say this is absorbance, and this is albumin concentration. Albumin in gram per liter. So if you plot the concentration of a known substance on here, of the standard on here, and you plot the absorbance on here, and if you recall back when you did this standard curve, you did serial dilutions of a standard, and you've plotted it on here, and you determine the absorbance of that, and then you had you obtained a straight line. Now you only did that for a limited amount of concentrations that you did the and the absorbance, but if you went higher, you will find that this result might curve somewhat. It might go that way, or you might get results that is very wide, very high there, very high there, and so you go on. And the same year, you might get results that differ extreme in extreme conditions. So, and let's say that result is there, that result is there, that result is there, that there, and that there. So you draw a line of best fit. Let's say you get some erratic results on top. So from this point to that point, you have a linear relationship. So for albumin, the low limit is let's say 2 grams per liter. They actually don't say it in here, but they say it in the next line. Sensitivity, it can be determined from 2.87 grams per liter. So for albumin, the linearity is 2.87 gram per liter to 75.5 gram per liter. To 75.5 gram per liter. So that is the range that is of this method that is acceptable. Any result above 75.5, the result is not acceptable. It must be diluted. Maybe a 1 in 2 dilution must be done. Then you're going to get a result that is half or around about within this range. And if you do a 1 in 2 dilution, you have to multiply the result with 2 to get your original concentration, or with a true concentration of your sample. Okay, that is linearity. Sensitivity, in other words, how sensitive is this method to detect? What is the lowest amount and the highest amount that this method can detect? So for albumin, the minimum detectable concentration of albumin is 2.87 grams per liter. So they don't say the highest amount that can be detected. Sometimes the method, this method can detect way up here. It can detect maybe 90 grams per liter, but that just means that it can detect 90 grams per liter, but it doesn't mean that it is acceptable within that range. So the sensitivity is from 2.87 gram per liter. It can be detected from. So then you can actually say that the linearity is from 2.87 to 75.5. Although I must caution you, in this case they don't give the lower limit for the linearity. They just give the upper limit of linearity. Okay, then other information that they give is precision. They've done precision analysis using serum. They've done intra-assay precision, and they've done inter-assay precision. And they've used 20 samples on level 2 and 20 samples on level 3. And that is the standard deviation and the mean that they got, and the coefficient of variation that they got, 1.28 and 0.71. And usually, and if you have a CV, coefficient of variation, less than 5, then you're sitting with a good precision. Anything greater than 5, then it becomes, your method becomes very imprecise. So the intra-assay is when they took 20 control samples of level 2 and they've analyzed it consecutively 20 times. They've analyzed it 20 times and they got this percentage C value. And they did the same with level 3. They've analyzed it 20 times and they got this. With inter-assay, this is not 20 times at the same time, at the sort of consecutively. It is on different days. So with inter-assay, it is between normal assays. So you've done maybe one control level 2, and then you do patient samples for an hour, for instance, or 2 hours, and then you do another control level 2, and then you do patient samples for another 2-3 hours, and so you go on. So over a couple of days, this level 2 and level 3 were analyzed 20 times, and the results calculated, the CV calculated, and found also good precision. Good precision for the inter and for the intra assay. Then they've also did a correlation study of this method, whereby they compared this method with another commercially available method for albumin analysis. They compared Randox albumin with, let's say, for instance, they don't say what it is, but let's say they used Beckman-Coulter albumin, and they compared the results that they got from here with results they got from there, and they did a calculation and they got a value of 0.999. Now, if the closer you get to 1, the better, more correlation is there between the two methods. So in this case, you almost have 1. So there is a good correlation between the Randox albumin method and the albumin method done with a different method. And they say 40 samples were analyzed, spanning between 16.6 gram per liter to 45.1 gram per liter. And furthermore, they give the references of the information where they got it from. Okay, that is it, folks. Thank you.